Here are solutions to homework set number 8 for ECE 476-676. This homework set looks at using interrupts and sensors, specifically a temperature sensor, to measure something, in this case, the temperature of a hot cup of water, and to find its thermal time constant. Now, the goal of this assignment is to measure temperature. For example, here's a hot cup of water with a DS18B20 temperature sensor. I can read that temperature with a Raspberry Pi Pico. If we measure the temperature over time, it should be decaying exponentially. This has a time constant. By measuring that time constant, it tells me how good the coffee cup is, how good of an insulator. What I'm using is just a plastic cup, not a very good insulator, which makes it easier to measure that time constant. So in terms of hardware, I just use a temperature sensor and a 52 Pi Pico board. In terms of software, I'll initialize the graphics display. I will initialize the temperature sensor, use interrupts to set the sampling rate to 1 second, and read the sensor actually 100 times, saving the data to a text file. So here's kind of what that looks like. Here's the Python program. What it does is it looks for the DS18B20 sensor. It turns on interrupts for 1000 milliseconds, or 1 second. Opens up a file, initializes the display, and then for 100 samples, wait for the interrupt to happen every 1 second. I will read the sensor, send the temperature to the LCD display, and the serial port. So here's what that looks like. It found the temperature sensor. Here is the reading, temperature in degrees Celsius, and that'll go on for 100 readings. And here's what that looks like on the display. I am displaying the time in seconds and the current reading in degrees Celsius. Currently these constants are going to be used later on. They're not being calculated. Okay, so that seems to be working. The next step is to collect some data. After I'm done collecting the data, it'll be saved to a text file on the Raspberry Pi Pico. Here's what the text file looks like. If I plot it, there's my temperature versus time. That should be a decaying exponential. Sort of. Sometimes it helps to collect a set of data, look at it, wait for it to settle out, collect some more data. It does help if that cup of water is really, really hot. So I have a bigger slope initially. That leads on to problem number 3. I would like to measure the thermal time constant. This is decaying as B e to the minus AT. Find the time constant A. Or find A, time constant is actually 1 over A. To do that, I can use least squares. So I'm going to set it up as in the form of y equals ax plus b. Y is the log of temperature minus T ambient. X is your time in seconds. And then your constants are A and B. If I set this up as matrix Y, matrix B, I can do least squares curve fitting. A is B transpose B inverse B transpose Y. B transpose B is this matrix. B transpose Y is that matrix. So in Python, I can set up the B matrix, take the previous solution, add to it x squared, x and 1, where x is time. My Y matrix is x times y. Y is the log of T minus T ambient. T ambient is the temperature that I measured. As I compute, as long as I'm past the second data point, I can invert the B matrix and compute my constants A and B. The time constant is just minus 1 over A of 0, 0. I will then display that on the LCD display. Yeah, let's try that again. And as it's running, it's got the temperature of the cup, the ambient temperature that I hard-coded, and as it runs, every data point it updates your least squares curve fit for A as your time constant in seconds, and B, just how much the temperature is above ambient. and also displays it on the shell window. Time, temperature, time constant, and B. Now running it, I actually ran it 4 different times. Here's the data. Looks reasonably good. Kind of see decaying exponentials for each one. At the end of each data run, I've got my 4 time constants. Not real consistent. I can start doing some statistical analysis. So I've got 4 data points as a mean, standard deviation. The 90% confidence interval for the next data point, the next reading, will be the mean plus or minus 2.35 standard deviations. This is the t-score for 5% tails with 3 degrees of freedom, meaning sample size of 4. So I'm going to be 90% certain my next reading will be somewhere in this range for my time constant. There is a thermal time constant for this coffee cup. Coffee cup right here. What it is, I don't know. As I get more and more data points, I'll have a better measurement of it. With sample size of 4, I divide the variance by the sample size, meaning divide the standard deviation by the square root of sample size. The actual time constant is somewhere in this region with a probability of 0.9. So that is homework set number 8 for Advanced Embedded Systems.